Hey everyone, welcome back, I guess, to school, even though you're not here. I know it's not the best situation, but I just wanted to let you guys know we don't have hardly anything left to cover. So you guys are in a really good spot for the AP exam. I'll give you some more resources to help you guys study when it gets closer, but we're not going to know anything until April 3rd. That's when they're going to release all of their information. So for now, we're going to finish chapter 19. You guys have a lot of the information already. Like we've kind of touched on a lot of this stuff in other units. And I think you'll come to see that a lot of it's common sense. So I'm just going to review what we went over. I know it's been about a week. We were talking about the greenhouse effect, and we also talked about how climate changes naturally and how it's also changing due to human impacts. So for the warm up today, I had you guys look at the volcano and temperature graph here. What you should have seen is that every time there's a really big volcanic eruption, we get a dip in temperature. Why is that? Well, if we take a look, and I know I don't have this blown up very large, but if we take a look at this picture, we can see that when there's a volcano, we get a lot of ash and sulfuric acid. So remember we talked sulfur comes out of volcanoes. You guys know that if we take a look at a different picture here, we can see the sulfur here. And the problem with that, not only is it an air pollutant, but when it mixes with water, it actually forms these little droplets and these little aerosols. So these little particles, and all of these particles reflect light. So basically it's making a big haze, cloud, ash of stuff, and it reflects light. So the sunlight can't get through to the ground, and that's why volcanoes and sulfur in general has a cooling effect. So that's one example of how the climate can change naturally is through volcanoes. They block some of the incoming UV radiation. We talked about the greenhouse effect. We know that the greenhouse effect is natural as well. However, humans have caused it to increase. So we said, we colored this little picture. We said it's UV light that comes in. So you need to know that it's UV light coming in. And then once it hits something, it turns into infrared radiation. And infrared radiation is heat. So it hits the ground and some of it bounces back and gets through the greenhouse gases to space, but some of it's reflected. So the greenhouse gases act like a blanket and they trap heat inside of the earth. So we talked about how, let's see here, I don't think we filled this in. This is at the bottom of that picture that we just looked at. And one of the things that I frequently see asked on the AP exam is what's the most common gas in the air? Now, that's more of a question that I've seen on the older AP exams, but I would just put a star by it. So 78% of the gases in our atmosphere, it's not oxygen, it's not carbon dioxide, it is actually nitrogen. So if we go back to the nitrogen cycle, you'll remember that nitrogen can't just go into the ground by itself. It needs help from bacteria or lightning. Greenhouse gases, carbon dioxide, and a bunch of others, they're not even listed on here. So they're only a tiny, tiny amount of our atmosphere, but they have a really big impact. So you can see nitrogen and then oxygen. So nitrogen 78%, oxygen 21%. Yesterday, I had you guys look up a bunch of greenhouse gases using the article. So we'll just, let's see here. Wonder where my greenhouse warming potential slide is. Oh, there it is. Okay, great. Let's write down greenhouse warming potential then, because it's next on your note packet. So greenhouse warming potential, it's a long definition. I'll give you a second to write it down, or you can just pause the video here. So it estimates how much a molecule of any compound can contribute to global warming over a period of 100 years relative to a molecule of CO2. Super wordy. All right. Here's what it's saying. It's saying how much is a molecule going to warm the Earth? And we're going to compare it to CO2. Okay. So how much can this molecule warm the Earth over a period of 100 years if it's stuck in our atmosphere? You'll notice Carbon dioxide has a global warming potential of 1. Okay, so the global warming potential is 1, and that's because we're always comparing it to CO2. So if we compare CO2 to CO2, it's going to be 1. It's going to be the same. All right. Methane, and if you don't have this filled out in your chart from the article yesterday, just fill out the global warming potential. Methane is 21, so it's a higher warming potential. So it's going to warm the atmosphere 21 times more than CO2. So methane is going to cause our temperature to increase significantly more than CO2. Nitrous oxide, 310. So compared to CO2, it's going to cause the Earth to increase, or the molecule will cause warming 310 times greater than CO2. Now take a look down here. Hydrofluorocarbons, that's the same as fluorinated, some of these fluorinated gases. You'll see lots of different, actually HFCs, yeah, that's a type of them. You'll see there's a wide range. It's because there's lots of different ones. We talked about bromine, compounds that contain bromine or fluorine, but these are the CFCs that we looked at with the ozone depleting. And then you see 2 other ones that are actually larger. I don't usually see any of these on the AP exam, so I'm not going to talk about them. So this is the global warming or greenhouse warming potential. I'm going to go back. These are our greenhouse gases. I'm just going to skim over them because we talked about them, or you guys looked it up on the website yesterday. So water vapor is the most common. Water cycle, think about it. Water's in our atmosphere. The thing is, though, the water cycle is really quick, so it doesn't last very long. It either will form clouds, it'll condense, it'll go into rain, it'll precipitate out, and then go into the ground. So water vapor doesn't last thousands of years like CFCs. So we have CO2, we've got methane, nitrous oxide, ozone, and then CFCs. Remember, we talked about the CFCs before. Beautiful. So now what we're going to do, we're going to look at this chart. So which greenhouse gas lasts the longest in the atmosphere? So if we take a look here, we have the concentration, global warming potential, that's what we just talked about. How much potential does it have to warm the Earth? And duration. So which one lasts the longest? CFCs, right? So for the first question there, CFCs last the longest in the atmosphere. They last 55 to 500 years. And again, if you're talking some of the other types of these, like hydrofluorocarbons or hydrocarbons, or HFCs, hydrofluorocarbons, they will have different time ranges as well, but they're long. Shortest you can see is water vapor, right? We just talked about that. And which one has the most warming potential? That would be CFCs. So that's why it's most important to regulate these CFCs, and that's why we'll talk about the legislation, but they've basically banned the use and the manufacture of CFCs because they destroy the ozone, they have a huge warming potential, and they last a long time. The one thing that I need to make sure that you know is that of all of these, I don't think we wrote it somewhere, but if you flip back to your previous page where you have that chart where it says fluorinated gases, you might want to write down that CFCs or fluorinated gases are man-made. They're one of the very few that's only man-made. It only comes from a man-made source. So ozone, we talked about tropospheric ozone, that can be man-made, but ozone's also in the stratosphere. Water vapor, that can be created by natural processes. Nitrous oxide, that can be created in the nitrogen cycle by natural processes. Same with methane, waterlogged soils, and CO2. So the only one that's exclusively man-made is CFCs. All right, so we're going to talk about some trends, and then tomorrow we'll probably do feedback loops. So, all right, so I had these slides these are the slides I redid, so we're going to skip those. I'm also going to skip where do greenhouse gases come in Wisconsin, and we're going to go to climate change history and trends. So in 1988, the UN stands for United Nations, created the Intergovernmental Panel on Climate Change. So you'll see this referred to, the IPCC. You'll hear that a lot in papers or news articles or stuff like that. So it's 3,000 scientists from around the world. They study climate change. They issue a report every year, and they have big conferences, and it's this whole world effort to basically curb climate change. So they formed this group. And the reason they formed this group is because of all of the trends that they were seeing in the data, and we're going to look at some of these trends. So one guy, Charles David Keeling, he measured CO2 levels in Hawaii. Think about why we would want to measure them in Hawaii. Just take a second. So the reason we want to measure them in Hawaii is not by anything. If we were to measure them in Los Angeles, it would be tainted by all of the city traffic. Sure, Hawaii has cities, but it's a lot less populated, and it's away from a lot of other cities or sources of carbon dioxide. So Hawaii is kind of in the middle of nowhere, so you can get a pretty good idea of what CO2 levels are. So he found that CO2 is increasing. Why? Well, we know that humans are burning more fossil fuels, we're using more of them. We're going to look at this curve though. So this curve is sawtoothed. And if you notice, every year it goes up and down, up and down, up and down for every year. So if we're measuring CO2, why would it increase during one part of the year and decrease during another part of the year? So if you think about it, we're going to have more carbon dioxide. The carbon cycle changes depending on what type of environment you're in or what time of the year, what season. So if we're talking about the winter, we're not having a lot of carbon cycle action going on. If we're talking about summer, okay, we've got a lot more CO2 being cycled through the atmosphere. So the reason it's sawtoothed is because CO2 cycles faster in the summer. So plants are doing photosynthesis, they're doing cellular respiration, so they're going to be producing and releasing more CO2. So the curve goes up and goes down based on how much CO2 is being released. So that's one of the things I've seen them ask before on an AP exam. And again, just to reiterate, if you think about it, when you guys think the CO2 would be the lowest? Would it be in winter or would it be in summer? So this is one, I'm not going to lie, I have to look up every time. But in the summer, plants are doing more photosynthesis. So yes, they're still doing cellular respiration and releasing CO2, but the photosynthesis is taking in more CO2. So it actually decreases in the summer. So the bottom of the curve here, this is going to be summer. The top of the curve is going to be winter. So let's look at some other trends. Which country has the highest CO2 emissions overall? So this would be overall here on this left side. No surprise there, China, right? Lots of manufacturing, lots of people, lots of transportation, lots of cars, okay? Maybe not as many cars, but you get the idea, lots of industry. United States is second. If we do it per capita, you guys remember what per capita means? Per capita means per person. So per capita, oh, surprise, the United States. Why? Well, cars. We own more cars and we drive more than pretty much any other country. So CO2 emissions per capita is the United States. So we're going to look at how they determine how much CO2 and what the temperature was in ancient times. So I'm going to play this. Hopefully it all plays correctly through this recorder. It's only 2 minutes, so.
It's a busy, freezing cold day inside the National Ice Core Lab in Denver, Colorado.
We're going to cut gas samples out of this core.
Scientists from Maine to California here to cut pieces of precious Antarctic glacier ice to take back to their labs for study.
We started the Ice Core project in 2005.
With support from the National Science Foundation for a project called the West Antarctic Ice Sheet, or WAIS Divide, lab manager Mark Twickler and a team of scientists, engineers, and support personnel traveled to the bottom of the world to drill out and bring back these ice cores. The goal of the project? To collect and study perfectly preserved records of the distant past.
The unique things about polar glaciers is each year that it snows there, the snow never melts. So you get 1 year of snow on top of the next year of snow. It compresses, so everything that fell out of the atmosphere, dust, salt from the ocean, volcanic ash, is preserved in that ice core.
This particular ice sheet is more than 70,000 years old. The team drilled down more than 2 miles into it to retrieve these cores, which were then flown to the U.S. and stored in a giant 40 below zero freezer here at the Ice Core Lab.
Inside this freezer contains more than 10 miles of ice cores collected from around the world.
Twickler says the ice core's layers are like tree rings, each layer representing a year of weather and snow.
We can tell what the temperatures were. We can tell how rough the oceans were around Antarctica. We can tell how dusty Australia was.
Scientists are keen to study the bubbles trapped in the cores, each a tiny pocket of air frozen in time.
We can measure a variety of gases that were in the atmosphere at the time the bubbles were formed.
Other scientists want to know how ice sheets melt over time.
We don't necessarily have a really good handle on how the ice sheet as a whole will respond in a case of changing climate.
Twickler says this icy blast from the past is helping researchers better understand the mechanics of climate change, and that in turn will help them make better predictions as to what a changing climate may mean for our future. For Science Nation, I'm Miles O'Brien.
So, what are ice cores used for? They use these ice cores in order to look at history of carbon dioxide levels and temperature. So this is how they know what the CO2 levels have been in the past, or what the temperature has been in the past, because they can take these little bubbles that have different types of gases in them, and they can quantify and record what are the different types of gases, how much of each of them, how much dust is there, and they have a perfectly preserved record of that climate. So they use this to figure out and go back in time to figure out what the climate was like in the past. And this is where they've gotten a lot of their data on climate change. So since 1880, global temperatures have increased 1.4 degrees Fahrenheit or 0.8 degrees Celsius. And that might not seem like a lot, but for a lot of species, it is significant. So things that are impacted, coral reefs are really sensitive to temperature changes. There's a lot of other types of animals and plants that are really sensitive to small, minor changes. You can see since 1890, here's our temperature. Again, this graph looks really scary. If you look at the axis, it seems a little less scary, right? 0.6 or 0.8 degrees. But we're on track to definitely continue increasing. The 10 warmest years on record since 1880 have all occurred between 1998 and 2013. That's kind of an outdated figure. I'm guessing I took that from the book, and the book has been published. I don't remember when the book was published, but basically the 10 warmest years on record have all been in the last 20 or 30 years is what you need to know. So our warmest years on record, we're having a lot more record years and record rainfall and record weather events. Put a big star next to the next two, these questions, these two. They like to ask about these types. I've seen these multiple times on AP exams. So if we take a look, red, these are degrees Celsius. So how much on average have these different parts warmed? So red, we've got 4, orange is 2, yellow is 1, tan is 0.5, and then blue means they've cooled. So which parts of the world have warmed the most? You will see it's up towards the Arctic, right? probably the Arctic Circle. And this is where you'll see a lot of times you'll see advertisements or like save the polar bears and a little polar bear on like, you know, a little tiny iceberg. Well, polar bears live in the Arctic, okay? They don't live at the South Pole. So we have a lot of warming going on up here. And then which parts have cooled the most? Cooled the most, there are actually parts of Antarctica that's cooling. And if you look, white is actually right around 0. There's other graphs that show this better, but a lot of parts of Antarctica, some parts of Antarctica have actually been cooling. All right, so that's where I'm going to stop today. Tomorrow we'll just do feedback, so it'll be short, and then I'll probably give you a short little sheet to do. So I hope you all are doing well, and I miss you, and have a good rest of your day.